Have you ever stopped and wondered what is actually happening, on a microscopic level when you wash your hands? It turns out there's some pretty incredible, totally invisible chemistry at play in our most common cleaning products. So, let's dive in and uncover the science that keeps our world clean.
Okay, first things first, let's start with a problem that I know we've all faced. You got a greasy pan, oily hands, whatever it is, and you run them under the tap. And what happens? The water just kind of beads up and rolls right off, leaving all that grease behind. So what gives? Why can't plain old water get the job done?
Well, the answer, the culprit, if you will, is something called surface tension. See, water molecules are, they're a bit clingy. They're super attracted to each other, and they create this tight-knit barrier on the surface. This molecular teamwork is so strong that it literally prevents the water from mixing with oil or grease. They just can't break through that barrier to wash the grime away.
But don't worry, because where water fails, we have a chemical hero that's ready to save the day. It's this tiny little supermolecule that is specifically designed to break down those barriers and make cleaning possible.
And this hero is called a surfactant. The name itself is actually a huge clue. It's short for surface active agent. Its entire job is to get active right there on the surface of the water, break that tension we were just talking about, and finally allow water and oil to interact.
So how in the world does this one little molecule work? Well, it has kind of a split personality. One end is what we call the hydrophilic head. Hydro for water and philic for loving. So this part is totally drawn to water. But the other end is the hydrophobic tail, phobic for fearing. This part is repelled by water, but it is very attracted to oil and grease.
And here's where those two personalities work together in a brilliant three-step mission. First, the oil-loving tails dive in and attack, grabbing onto any particles of grease and dirt they can find. Then, all the surfactant molecules surround the grime, forming this tiny little sphere called a micelle, with their tails pointing inward, trapping the dirt. Finally, the water-loving heads on the outside of that sphere allow the whole package, dirt and all, to be carried away by the water. And just like that, the grease is gone.
Now, not all cleaning jobs are the same, right? And because of that, not all surfactants are the same either. Chemists have actually developed different types, each with its own special skills, and they generally fall into four main categories, all based on their electrical charge.
First up, we've got anionic surfactants. You can think of these as the powerful workhorses of the cleaning world. You'll find them in things like laundry detergent and dish soap. When they dissolve in water, the part of the molecule that does the heavy lifting has a negative charge. It's an anion, and this charge makes them absolutely excellent at lifting and suspending dirt.
Next are the cationic surfactants. In this case, the active part of the molecule has a positive charge, a cation. Now, this positive charge doesn't make them great cleaners, but it does make them fantastic fabric softeners and disinfectants. That's because they can stick to negatively charged surfaces, like your hair or your clothes, leaving them feeling super smooth.
Then we have the neutral players, non-ionic surfactants. As you probably guessed from the name, they have no electrical charge at all. This makes them less reactive to the minerals in hard water and makes them incredibly good at emulsifying oils, which is just a fancy way of saying they're great at breaking down oils and mixing them into water. That's why you'll often find them working right alongside anionic surfactants in laundry detergents to tackle really tough, greasy stains.
And finally, we have the most versatile of them all, amphoteric surfactants. These are the true shapeshifters of the group. In acidic water, they'll act like a positive, cationic surfactant, but in alkaline water, they'll behave like a negative, anionic one. And in neutral water, they're non-ionic. This amazing adaptability makes them very gentle, which is perfect for personal care products like shampoos and hand soaps.
Okay, so now that we're all experts on surfactants, let's clear up one of the most common points of confusion in the cleaning aisle. What is the actual difference between soap and detergent?
You might have heard this classic chemistry riddle before. It sounds a little confusing, I know, but once you understand surfactants, it makes perfect sense. Let's break it down.
So here's the key. Detergent is the big, broad, scientific term for any surface active agent. Soap is just one very specific type of detergent, one that's made from natural sources like animal fats or vegetable oils. Most of the cleaning products we use today, though, use synthetic surfactants. They're still detergents, but they are not soap. And the big advantage of these synthetic detergents is that they work really well in hard water, which is full of minerals. Traditional soap, on the other hand, reacts with those minerals to form that familiar, really annoying soap scum.
But the story of this invisible chemistry, it doesn't just stop with cleaning.
Surfactants are a key player in a much bigger industrial process, especially when it comes to the clothes that we wear every single day.
You see, in the textile industry, surfactants don't work alone. To create vibrant, long-lasting fabrics, you need a whole team of chemical helpers, and they're called auxiliaries. Think of surfactants as the ones who wash and prepare the fabric, getting it all ready for the rest of the team to do their jobs.
One of the first players on that team is a swelling agent. These chemicals literally open up the pores of the fabric fibers, which makes it way easier for dye molecules to get deep inside for a really rich, even color.
Then you've got optical brightening agents. Now, these don't actually make the fabric any cleaner. What they do is they absorb invisible ultraviolet light and then shoot it back out as visible blue light, which totally tricks our eyes into seeing the fabric as whiter and brighter than it actually is. Pretty clever, right?
Now, if the factory is using hard water, those metal ions like calcium and magnesium can really interfere with the dyeing process. So they add sequestering agents to basically grab onto these ions and take them out of play, making sure the dye can do its job properly.
And believe it or not, even something as simple as salt plays a huge role. In the dyeing world, salts act as an electrolyte. They essentially push the dye molecules out of the water and force them onto the fabric, which makes the whole process way more efficient.
So when you think about it, from the soap you use to wash your hands, to the detergent that cleans your laundry, all the way to the complex chemical treatments that created the very clothes on your back, this invisible world of surfactants and auxiliaries is all around us, constantly working behind the scenes.
It really makes you think, doesn't it? The next time you see suds in the sink, you'll know it's not just bubbles, it's a microscopic battle being won. So, what other hidden science is out there, quietly making your daily life possible? Thanks for watching.